Hi, I'm Rowan from Vantage Admissions. In this video, we're going to work through an exercise which is particularly instructive for the probability and statistics section on STEP. One of the recurring themes on STEP questions is that ideas you're familiar with will be combined in unfamiliar ways. In this particular exercise, we're going to consider a binomial distribution and a Poisson distribution, two distributions that students preparing for STEP should be familiar with, and consider what happens when, in some sense, these distributions are composed together. I really like setting this exercise to my students because there are so many transferable lessons which can be extracted. Here's the setup of the problem. Bob plays a game at a fun fair in which tickets can be won. The number of tickets which he wins, x, obeys a Poisson distribution with parameter lambda. Now, if you don't know about Poisson distributions yet, do learn about them for STEP. All you need to know is that if I say a random variable x has a Poisson distribution with parameter lambda, I'm simply saying that the probability that x takes the value little x, so big letter for the random variable, little letter for a specific value it could take, is e to the minus lambda, lambda to the x, divided by x factorial, where x can be 0, 1, 2, or any positive integer. So, in other words, a non-negative integer. So that's all that means. Now, of the tickets which Bob wins, there is a constant and independent probability p that each ticket will actually then yield a prize. We want to think about the probability that Bob wins Y prizes and hence see what we can say about the distribution of capital Y, the number of prizes won. So the first thing that's kind of obvious here is there's something binomial about the problem, because once we have a certain number of tickets, I've got a constant and independent probability that each ticket, like a trial, will lead to a success, a prize. So one thing that's tempting to write down, and in some sense is true, is that y is clearly distributed binomially with parameter big X p, because each ticket won is like a trial, and then we have a constant probability p of success winning a prize from each trial. Now, why does that not just trivialize the problem straight away? Why are we not done? Well, you can't have a binomial distribution where the number parameter is itself a variable, right? So the point of a binomial distribution is the number parameter and the probability parameter are meant to be fixed constants. So this is not a true binomial because the number of trials is itself variable. It's as if we're feeding a Poisson distribution to a binomial distribution and asking about what comes out. So how can we make progress in trying to think about the probability that y takes a given value? Well, it would be very helpful if we knew how many tickets Bob had. If I knew that Bob had 5 or 6 or 7 tickets, under that assumption, I really could say that the number of prizes he wins is binomial distributed with that many trials. So the trick we can play is we can split into cases according to the number of tickets which Bob wins. So in other words, I claim that the probability that Bob wins Y prizes can be written as a sum over cases according to how many tickets he wins. So if he's going to win prizes, he needs to win at least Y tickets, and there's no upper limit to how many tickets he could win because he might get loads of non-prize tickets. So there's no upper limit, but he definitely needs to win at least as many tickets as he's going to win prizes. And I can do the probability that he really does win that number of tickets times the probability that he wins that many prizes given he had that many tickets. So you can think of it as if we have a probability tree where the first branch is for how many tickets he wins, and then the subsequent branching is for how many prizes he wins given that he had that many tickets. So clearly these probabilities are just binomial with number parameter equal to the relevant x. So I'm not doing anything profound here. All I'm really doing is thinking about a probability tree where the first branch was how many tickets he won. Obviously, we could even have a branch where he won no tickets. Now, a formal way of putting this is as the law of total probability. So although you wouldn't be expected to know this result in this language for STEP, it's fine to just think of it as being something that comes from considering a probability tree. It's nice to know the result that in general, the probability X happens can always be written as the sum over the probabilities for the different A's times the probability of X given that A, summed over the A's, where the A's are mutually exclusive events, so you can't have more than one, of which one must occur. So in other words, one and only one of the A events will happen, like AI might be Bob wins I tickets, right? So that's the example we've used here. So although the law of total probability is not something you're officially meant to know, because all we're really doing is applying the logic of probability trees, it is something that they can expect you to use in a hard part of a STEP problem. So let's now see if we can evaluate this expression. So it should be easier to make progress now, because all of the terms inside the sum are probabilities for which we understand the distribution. The probability X equals X is the probability Bob wins X tickets. That's fine because X is Poisson distributed. And the probability that he wins Y prizes given that he had X tickets is easy, because if it is the case that he's got little x tickets, the number of prizes is binomial distributed little xp, because I've got x trials tickets with a constant probability p of yielding a prize. And this is a true binomial distribution because now the number parameter is fixed. So I can easily write down these probabilities. So using the result that I told you for a Poisson distribution, the probability that x is e to the minus lambda, lambda to the x, divided by x factorial. And this probability, I can just use this distribution. So it's going to be x choose y, p to the y, 1 minus p to the x minus y. Now we're far from done. We can't leave our answer as an infinite sum. We need to find a way to evaluate it. But the evaluation of series is very often what probability and stats questions will boil down to. And there are nice recurring tricks we can use. In particular, very often, if we have an infinite series which is not geometric, the most common technique we'll use to evaluate it is usually to spot that we can manipulate it into the form of the Maclaurin series of an exponential. So a fact that you need to know is that e to the z can be written as sigma z to the r over r factorial summed from 0 to infinity. So this is the Maclaurin series for the exponential function. And a very common trick for evaluating infinite sums in probability and stats is going to be to manipulate things into this form. Let's keep that in mind. So the first thing I'm going to do is expand this in terms of factorials. Now, on the other hand, sometimes when you have a sum with an n choose r, the way you'll evaluate it is trying to manipulate your sum into the form of a binomial expansion. So into the form of the binomial expansion of a plus b to the n for some a, b, and n. That doesn't seem likely to succeed here because this is an infinite sum. But if it were a finite sum, that might be a line of attack worth pursuing. Here, because it's infinite, I'm just going to expand that in terms of factorials. So let's do that first, and then we'll pull out any constants that don't depend on the counter variable to try and simplify the remaining sum. So x choose y is x factorial by y factorial, x minus y factorial, and then I've still got all the other bits. Now, it's quite nice that the x factorials cancel. X is, of course, the counter variable, so x is the complicated thing that can't be pulled out of the sum. Any cancellation of x terms is thus extremely welcome. So let's pull out what we can. We'll pull out the e to the minus lambda, we'll pull out the p to the y, and we'll pull out the y factorial, because none of these things depend on the counter variable x of the sum. What I'm then left with is lambda to the x over x minus y factorial, 1 minus p to the x minus y. Now, bearing in mind our broad strategy that we might like to try and get something like this Maclaurin series, the most obvious issue is that our sum starts from y, whereas the Maclaurin series starts from 0. We can easily remedy this by making a simple change of variables. So why don't I write r equals x minus y? So all I'm doing is I'm relabeling the counter variable used to define the sum. It's just a dummy variable, it's a stand-in for the values it runs over. So I can always shift it down by a number, say by y, and as long as I update my summation bounds such that this is capturing the same values this was, then we've got the same sum. So in particular then, as x runs from y to infinity, r is going to run from 0 to infinity. Because clearly r is smallest when x is smallest. When x is y, I get 0. And then x ran over all the values from y to infinity. So that means that r will run correspondingly over all the values from 0 to infinity. So I've just rewritten the summation. Now lambda to the x, well, under this identification, x is r plus y. So that becomes lambda to the r plus y. X minus y factorial is just r factorial, and 1 minus p to the x minus y is just 1 minus p to the r. So this is starting to look a lot like our Maclaurin expansion now. Now the main issue is that I would like to bunch this together as one power, but I've got y more of the lambdas. That's no problem. We can just pull a lambda to the y out of the sum. That doesn't depend on the counter variable r. So if I pull out a lambda to the r, I can promote the p. Sorry, I pull out a lambda to the y rather. I'll promote that p to the y to be p lambda to the y now. So it's p to the y and lambda to the y. I've still got my over y factorial. And now my sum reads lambda to the r 1 minus p to the r. So I can write that as lambda 1 minus p all to the r over r factorial. And now our plan has come to fruition. If you compare with the Maclaurin expansion for the exponential, this is simply e to the lambda 1 minus p. So by recognizing that Maclaurin expansion, we've evaluated the sum. And now we just need to process the algebra and see if it will simplify. So I've got e to the minus lambda, p lambda to the y, over y factorial. I'll expand this out to try and cancel with the e to the minus lambda. So that's e to the lambda, e to the minus lambda p. These cancel, and what I'm then left with is e to the minus lambda p to the y, so I'll write that as lambda p for consistency, divided by y factorial. So this is our expression for the probability that y equals y. But hold on a minute, this is exactly what I wrote down earlier for a Poisson distribution's probability, except rather than lambda, I've got lambda p. So we can see therefore that y is distributed Poisson with parameters lambda p. I mean, note also that the number of prizes can run over the values from 0. You could win no prizes up to infinity because there's no upper limit. So it runs over the same values and it's got the correct probability formula. So what we've seen is that if in general, so you don't need to memorize this result for step, but the general result we've proved is that if y is distributed binomially with parameters xp, where x is distributed by Poisson rather, with parameter lambda, then in fact, y is distributed Poisson with parameter lambda p. So it's a really nice, simple result for the composition of a Poisson and binomial random variable. So the techniques we've exhibited in this exercise are really transferable. This idea of splitting into cases in your probability calculation, which is really just the use of a probability tree, but which can be termed the law of total probability, that's really transferable. Also the idea that we'll often want to manipulate an infinite sum into the form of a Maclaurin series. You'll see lots of applications of these tricks as you work through STEP problems. Like so many topics in STEP, probability and statistics can appear very intimidating at first, because the questions seem so different from what you'll be used to seeing in school. But with perseverance, you will see that many of the tricks and ideas recur again and again, including those which we've used in this video. If you'd like to see more STEP videos, do remember to subscribe. The problem we've worked through today is taken from our STEP preparation programme, a course which may be suitable for those planning to take a particularly intensive approach to their STEP preparation. If you'd like to learn more about this programme, do remember to visit our website. And thank you very much for watching.